So what very often happens when one tries to solve a partial differential equation is we reduce it to an ordinary differential equation. But that is only useful if we know how to solve an ordinary differential equation. So that's what we're going to talk about for the next couple of classes. I already had uploaded some notes on ordinary differential equations to the website. I also just uploaded what will be a second textbook for our course, a set of lecture notes on partial differential equations. It's not very long, about 150 pages. It's basically a book. And you don't have to buy it because I just put it on the website so you can see it on Blackboard. Let's talk about ordinary differential equations. So our general notation will be, oh, sorry, before I start, are there any questions? There was some homework due today on lessons 1 and 2 from the Farlow book. Is there anything I should go over there? If not, then, okay, we'll start ODE. And at any time, sorry, not at any time, but at the beginning of every class, I ask for questions. And you can ask questions about homework problems, whether they're new homework problems or old homework problems, or anything in the text as well. So we're going to look at ordinary differential equations where you can isolate the first derivative. This is a first order differential equation, y prime equals f of x, y. So this is a first order ordinary differential equation. And the first order means that we have the first derivative of the unknown function, but no higher derivatives. And suppose we have the differential equation. So this is always the fundamental example, y prime equals y. So this is a differential equation. This is an ODE. But we also have an initial condition that we want to find a solution y equals f of x with f of x equal to some number c. So this is what is called the initial condition. F of 0 is equal to c. So the initial condition doesn't have to be a value of the function when x is equal to 0. It can be any number, but it's simplest and there's no reason not to always consider the initial value at 0. So what is one solution? One solution is the function f of x equals c e to the x. This is one solution because, first of all, if you differentiate f prime of x, you get the derivative of c e to the x, which is c e to the x, which is f of x. And f of 0 is c e to the 0, which is c times 1, which is c. So this is one solution. And we claim, so this is a kind of a theorem, this is the only solution or the unique solution of this differential equation with this initial condition. And how do we prove it? Well, the simplest way to prove it is say, okay, suppose we have any solution. So let g of x be any solution of g prime of x equals x and g of 0 equals c. We must show that in fact g of x is c e to the x. Or equivalently, going to show that if we look at the function g of x e to the minus x, that's equal to c, right? This equation is the same as this, just multiply by e to the minus x. So suppose we let h of x be equal to g of x e to the minus x. We want to show this is a constant. How do you show a function is a constant? A function is a constant, certainly if its derivative is 0. So let's differentiate. H prime of x by the product rule, this is g prime of x e to the minus x plus g of x times the derivative of e to the minus x, which is minus e to the minus x. But g prime of x, what is that? G prime of x is c e to the x. Sorry. Yeah. So if g of x is c e to the x, g prime of x, this is c e to the x times e to the minus x. Minus g of x, c e to the x, e to the minus x, we get 0. Which means h of x is a constant. What is h of 0? It's g of 0 e to the minus 0. G of 0 is c, and e to the 0 is 1. So if h is a constant, and its value at 0 is c, h of x is equal to c for all x. So this is our first example of an existence and a uniqueness theorem. If we have the differential equation, y prime equals y, with an initial condition, this equation has a solution that satisfies the initial condition, and there's only one. The solution is unique. So this is maybe the most important theorem in differential equations because it's the simplest and it's central to everything that goes on. Now, let's look at more generally first order linear ordinary differential equations. So a first order linear differential equations has the following form. Y prime plus some function of x times y is a function of x, is some function q of x. And we want to know, so this is a first order linear ordinary differential equation. Can we solve it? And if you have a given initial condition, can you solve the ordinary differential equation with the initial condition? And is the solution unique? So let's start with a special case, which is when the right-hand side of this equation, q of x equals 0. So in that case, we have what is called the homogeneous first order ordinary differential equation. Y prime plus p of xy equals 0. Now, I also have to specify, when we ask for a solution of this differential equation, we might want a solution which is valid for all x, or we might want a solution which is valid only for some interval, I. I could be the whole line, or it could just be a finite interval. So let's say we're looking for a solution on an interval I. Suppose y is not equal to 0 on the interval I. That means you can divide by it. So if I have this equation, y prime plus p of x y equals 0, I can rearrange it. Y prime is minus p of x y, or dividing by y, because y is non-zero, 1 over y, y prime is minus p of x. So any non-zero function y that satisfies our homogeneous first-order linear differential equation also satisfies this equation. So suppose y is not only non-zero, but suppose y is positive. In that case, the logarithm of y is defined, and 1 over y, y prime is exactly the derivative of the natural log of y. When you differentiate this by the chain rule, you get 1 over y, y prime. So what we have is 1 over y, y prime, which is the derivative of the logarithm, is minus p of x. And now you just integrate. That means that the log of y is minus the integral of p of x dx, some particular solution, plus a constant. And now you just exponentiate, you get y is e to the minus p of x, minus the integral p of x dx, plus c. Okay? So you can solve this first order homogeneous linear ordinary differential equation with just one integration, right? If you're going to have a positive solution. And if I want to follow the notes that I distributed last week, if I let a of x be equal to the integral of p of x dx plus c, then this is equal to e to the minus a of x, sorry, minus c. So every positive solution of my differential equation is of this form for some number c. Conversely, if you let y be e to the minus a of x, then by the chain rule, what is dy dx, or y prime? It's minus a prime of x times y. When you differentiate this, you get p of x. Which means that y prime plus p of xy is 0. So this says that this differential equation has a unique solution for any c. So we can state this, as does our notes, as follows. So if you look at the notes, this will be Theorem 8.2. So let P be a continuous function on the interval I. there exists a unique, so exists and unique. There exists a unique function y equals f of x such that y prime plus p of x y equals 0, and let me just add, so let a be a number in x and b be any real number such that y prime plus p of x y is 0 and f at a is equal to b. So if you're given this linear differential equation, homogeneous in first order and an initial condition, there's one and only one solution. And what is the solution? It's f of x equals b e to the minus a of x, where a of x is the integral from a to x of p of t dt. Proof. So let's show, first of all, that this is a solution. What do we know? P is a continuous function on the interval I, so you can integrate it. So for any x and I, the integral from a to x of p of t dt exists. That's a of x. So you look at f of x equals b e to the minus a of x. What is f prime of x? It's equal to the derivative of minus, this is just the chain rule, you're differentiating e to some function. It's minus a prime of x, b e to the minus a of x. When you, by the fundamental theorem of calculus, when you differentiate the indefinite integral, the derivative of a prime, the derivative of a of x is p of x. And this is f of x. So f prime of x plus p of x f of x is 0. And for this function, what is f of a? F of a is b e to the minus capital A of a. What is capital A of a? It's the integral from a to a of p of t dt, which is 0. So this is b e to the 0, which is b. So that is a proof that this differential equation with this initial condition has a solution. I've written it down exactly. Are there any questions about that? This is basically just freshman calculus. But you really have to know freshman calculus. So this proves existence. Existence. And how do we prove uniqueness? How do we prove that this is the only solution? Well, let G be any other solution of the differential equation with the initial condition. And consider the function h of x equal g of x e to the a of x. Let's differentiate it. H prime of x, by the product rule, is g prime of x e to the a of x plus g of x times the derivative of e to the a of x, which is a prime of x e to the a of x. I can factor out an e to the a of x, and I'm left with g prime of x plus a prime of x. What is a prime of x? P of x. But this is 0. So h prime of x is 0. So therefore, h of x is constant. What is the value of the constant? H of 0 is g of 0 e to the a of, h of a is g of a e to the capital A of little a. G of a is equal to b. Right? G satisfied the initial condition. And e to the a of capital A of a is e to the 0 is b. So this function h of x is constant, it's equal to b, which means g of x is b e to the minus a of x. So that is a proof of the existence and uniqueness of a solution to a first order differential equation. And we didn't have to assume anywhere in this proof that the function y or p of x was positive, non-zero, or even positive. We just did it.
I had a question.
Yes, go ahead.
So in the square parentheses, why is it 0 again? Can you just repeat?
Oh, because G is a solution of the differential equation. What's the differential equation? Y prime plus P of xy equals 0. So if you replace y by G of x, you get G prime of x plus P of x times G of x equals 0. G is a solution of the ordinary differential equation. So that means this is 0. And 0 times a positive number is 0.
Okay, and at the bottom it says h of a equals GAE.
H of a?
No. At the very bottom of the page, it's G. H A. Oh.
So H of a. So this is H of x. If I let x equal a, I get H of a is G of a e to the capital A evaluated at little a. This function capital A evaluated at little a is the integral from a to a of something. The integral from a to a is always 0. So this is e to the 0, which is 1. So this is b times 1, or b.
And also, just one more thing.
Sure.
When you have the section where it says proof, and you go f prime of x, and then it's equals, and it's negative p of x, f of x. So where's the f of x again coming from?
Okay, so here's my differential equation, right? And here's my initial condition. So I want to prove first that there is a solution of this initial value problem, and then I want to prove it's unique. So first I'm proving that there's a solution. And I just wrote it down. I said, let f of x equal this, where a of x is. And how did I get this? It's because when I was looking at the special case where p of x was a positive function, that's what I did on the previous page, I was led to this. In the case when I'm looking for a positive solution. So this is why I guessed, if you like, this would be a solution. How do I know it's a solution? I prove it. So I say, let f of x be equal to this, and then you see that it is in fact the solution of the differential equation, and it does satisfy my initial condition.
Oh, that's never mind. You just basically did like the double equals, but it's that equality where the 0 is, but you just carried it over. So f prime of x equals negative p of x, f of x, because
Yes.
before it was on one side of the equation.
Yeah, of course.
You
Yes.
did like a double.
Yeah, exactly.
Okay.
Let me see if I can do an example. Suppose I want to solve the equation y prime plus cosine x times y equals 0, and maybe y of 0 equal to 1. On the interval I, that'd be the whole real line from minus infinity to, actually, well, we'll worry about that in a moment. So in this case, my function p of x is cosine x. And a is 0 and b is 1. A of x is the integral from 0 to x, p of t dt. That's the integral from 0 to x, cosine t dt. The integral of the cosine is the sine. This is sine of x minus sine of 0, which is sine of x. So what is the solution of the differential equation? F of x is equal to b e to the minus a of x. B is equal to 1, e to the minus sine x. That's the unique solution of this differential equation with the property that f of 0, which is e to the minus sine of 0, which is e to the 0, is 1. So this function, e to the minus sine x, solves this differential equation. And it solves the initial condition. Okay. Suppose we have the differential equation y prime plus, I don't know, x squared y equals 0, and we want y of 2 to be equal to 3. Right? So I just made up a differential equation and I made up an initial condition, but there has to be a solution by our theorem. So in this case, p of x is just x squared. That's my p of x. A of x is the integral from 0 to x of t squared dt, which is 1/3 x cubed. So my function f of x is going to be, this should be from a, so a is equal to from 2. So this is 1/3 x cubed minus 1/3 2 cubed. So this is equal to 1/3 x cubed minus 8/3. So f of x is equal to b is equal to 3, e to the minus a of x. 1/3 x cubed minus 8/3. Or if you like, you can write this as 3 e to the 8/3, that's a constant, times e to the minus 1/3 x cubed. And what is f of 2? It's 3 e to the 8/3, e to the minus 1/3 times 2 cubed. This is minus 8/3, cancels this 8/3, we get 3. So for this differential equation, with this initial condition, we get this unique solution. Okay. Are there any questions about that? Okay, well, how about this? This is what I would do if we were in a physical classroom, but no reason why you can't try and do it at home. So here's a problem for you to do right now, wherever you are. All you need is some paper and something to write with. Solve the equation y prime plus, I don't know, 1 over xy equals 0, and y of, I don't know, 3 equals 6 on the interval I from 0 to infinity. So spend a couple of minutes right now and see if you can solve that differential equation. Well, let's see. Any success? So for this problem, P of x is 1 over x, A is equal to 3, B is equal to 6. Capital A of x is the integral from little a, 3, to x, 1 over t dt, which is just log x minus log 3. So f of x is b, that's 6, e to the minus a of x, e to the minus log x minus log 3. So this is 6 e to the minus log x minus e to log 3. E to the log 3 is 3. 3 times 6 is 18. E to the minus log x is 1 over x. So if I did this correctly, our solution of the differential equation is f of x equals 18 over x. Does it satisfy the boundary condition? Well, f of a, that's f of 3, is 18 over 3, which is 6, which is b. So the initial condition is satisfied. And what about the differential equation? So f prime of x, when you differentiate 18 over x, you get minus 18 over x squared, which I can write as minus 1 over x times 18 over x, because x times x is x squared. And 18 over x is f of x. If I bring this to the other side, f prime of x plus 1 over x, f of x, is equal to 0. So for that y equal f of x, y prime plus 1 over x times y is 0. So it checks. Pretty good. Any questions about that? That's okay. Well, hearing no objections, we will move on. So what we had solved completely is the homogeneous first order linear equation. y prime plus p of xy equals 0. But now I want to consider the non-homogeneous or inhomogeneous equation. The inhomogeneous first order linear ordinary differential equation. And so what we can do is, remembering what we did previously, for the homogeneous equation, we had the function a of x, which was the integral from a to x, p of t dt. Let g of x be any solution. Let's imagine there is a solution, or assume there's a solution. Be any solution of this ordinary differential equation with the initial condition that g of a is equal to b. Let h of x be equal to g of x e to the a of x. That's exactly the function we looked at in the proof earlier to show that the homogeneous equation had a unique solution. So let's look at this. Differentiate. The derivative h prime of x by the product rule is g prime of x e to the a of x plus g of x times the derivative of e to the a of x, which is a prime of x e to the a of x. If I factor out an e to the a of x, I have g prime of x, and a prime of x is p of x, p of x, g of x. Now, if g is a solution of this equation, g prime plus p times g is q of x. So what we have here is q of x. What we have is e to the a of x times q of x. So if we integrate from a to x, h prime of t dt, on the one hand, just from the fundamental theorem of calculus, this is h of x minus h of a. And that's equal to the integral from a to x of e to the a of t, q of t dt. And h of a, what is h of a? H of a is g of a, e to the capital A of a. This is e to the 0, which is 1. G of a is equal to b. So what we get is that h of x let me write it differently. So if g of x is any solution, and we let h of x be equal to this, then g of x, if I multiply by e to the minus a of x, h of x. What is h of x? H of x is equal to, this is minus e to the a of x. H of x is h of a, I'm just putting this on the other side, and h of a is b, plus the integral from a to x, e to the a of x, q of t dt. That is g of x equals b e to the minus a of x plus e to the minus a of x, the integral from a to x, a of t, q of t dt. Again, I'm trying to follow the notes that I distributed as closely as possible. So when you're studying at home, it's easy to follow. So what have we just done? We had the non-homogeneous first order linear ordinary differential equation. Y prime plus p of xy equals q of x. I said, suppose there is a solution, g of x. If there is a solution, then when we analyze this is what we did. We introduced the function g of x e to the capital A of x. We get g of x must be this. So if there is a solution, this is it. There's only one. So this says there is at most one solution. Let's check that it is a solution. So here, oops, let me move it down. Here is g of x. Let me differentiate. What is g prime of x? When I differentiate, I get b minus a prime of x, e to the minus a of x, plus, when I differentiate this by the product rule, it's the derivative of e to the minus a of x, which is another minus a prime of x, e to the a of x, times the integral from a to x, a of t, q of t dt. Oops. This is e to the a of t. E to the a of t. So the derivative of g, it's the derivative of the first term minus a prime of x times b e to the minus a of x, plus the derivative of the second term by the product rule is the derivative of this minus a prime of x e to the a of x times the integral, plus e to the minus a of x times the derivative of this, but again, by the fundamental theorem of calculus, this is e to the a of x, q of x. So g prime of x is equal to what? This is a prime of x minus b e to the minus a of x. What is a prime of x? P of x. So this is p of x times minus b e to the minus a of x. This cancels, that's a q of x, minus a prime of x, that's p of x again, e to the a of x, integral a to x, e to the a of t, q of t dt. This is p of x. I have a minus on, I'll take that out. So minus p of x times b e to the minus a of x plus e to the a of x, the integral from a to x, e to the a of t, q of t dt, plus q of x. This function is just g of x. So this is minus p of x, g of x, plus q of x. So g prime of x plus p of x, g of x equals q of x. So we have a solution of the differential equation, y prime plus p of xy equals q of x. And if in my expression for g of x, here it is, what is g of a? G of a is b, e to this, when I let x equal a, I get e to the 0, which is 1, minus, when x is a, this is 0. Sorry, plus 0, which is b. So this is my initial condition. So I proved that this somewhat complicated function I wrote down is a solution of the non-homogeneous differential equation with the boundary condition satisfied. And every solution must be this. This is the only solution. So we've just proved the existence and uniqueness theorem for non-homogeneous or for all linear first order differential equations. That's nice. Actually, it's very nice. Now, this is a 400 level math class. Means it's even more advanced than a 300 level math class. In 300 level classes, you learn to do proofs. So I expect that in a 400 level math class, you have some experience already with proofs, and proofs are what you do in mathematics. Right? If you're in physics, you don't worry so much about proofs, you worry about having the right equations and being able to solve them. And we're going to do both, but right now, we just proved existence and uniqueness for ordinary differential equations. Right? So there's a nice example at the end of this section in the notes that I gave out, and I'm just going to try and work through it. So here is the example. On the notes I distributed, this is on page 310. I mean, I only gave out maybe 10 pages of notes, but the pages are numbered. This is page 310. Find all solutions of the first order differential equation xy prime plus 1 minus xy equals e to the 2x on the interval from 0 to infinity. Okay. Now, you might say, wait a minute, there's a problem, because in the examples we've looked at, y prime wasn't multiplied by anything. And here, y prime is multiplied by x. Well, that might be a problem, but it's really not. Why is it not a problem? Because we're only looking at x from 0 to infinity. X is never 0 in this interval. So you can divide by it. So just divide by x. And we get y prime equals, sorry, y prime plus one minus x over y equals 1 over x, e to the 2x. Or if you like, y prime plus 1 over x minus 1y equals 1 over x, e to the 2x. So in the notation, we've been using y prime plus p of xy equals q of x. P of x is 1 over x minus 1, and q of x is 1 over x e to the 2x. And these functions are both beautifully simple and continuous for positive values of x. What does a of x equal? Suppose we just let a be equal to 1. We have to pick some a. So let a of x be equal to 1. So a of x is the integral from 1 to x, p of t dt. Is the integral from 1 to x, p of t is 1 over t minus 1. What's the integral of 1 over t minus 1? The integral of 1 over t is log x, and the integral of 1 is x. So it's this evaluated from 1 to, sorry, log t minus t from 1 to x. So this is log x minus x. And then when you evaluate this at t equal 1, this is 0, and this is 1, plus 1. Minus 1 is plus 1. So that's my function a of x. So e to the minus a of x is e to the minus log x plus x minus 1. This is e to the minus log x, that's 1 over x. So this is e to the x minus 1 over x.
Professor.
Yeah.
Is the minus switched or something in the initial equation when you did 1 over x minus 1?
So I have xy prime plus 1 minus xy equals e to the 2x. And when I divide by x, this becomes 1 minus x over x. And 1 minus x over x is 1 over x minus x over x, or 1 over x minus 1.
Oh, okay, yeah.
Right? So this is my p of x, 1 over x minus 1. Now, what's the solution of the differential equation? Here's the formula I had worked out. So let's call it f of x is equal to b, that's just the value of the function at 1, e to the minus a of x, that's e to the x minus 1 over x, plus e to the minus a of x, that's e to the x minus 1 over x, times the integral from 1 to x of e to the a of t. Well, e to the a of t, this is e to the minus, so just make this, just reverse the signs. This is e to the log t minus t plus 1 times q of t. What is my function q? 1 over x e to the 2x, which makes it e to the 2t over t dt. E to the log t is 1 over t is t. So let's just double check everything. This is the same as t e to the minus t plus 1 times e. And this t would cancel this t, and e to the 2t times e to the minus t is e to the t, and I have an e. So this is equal to this term, b, e to the x minus 1 over x, plus, I take out an e, this makes this e to the x over x, the integral from 1 to x of e to the t dt. So you have to know a little bit of, have to be able to do math, do a little bit of algebra. When you just work this out, this is exactly what you get. So f of x is equal to b e to the x minus 1 over x. When I integrate e to the t, I get e to the t. So this is e to the x over x times e to the x minus 1. Sorry, e to the x minus e to the 1, minus e. So this is b e to the x minus 1 over x, e to the 2 plus, write this neatly or more neatly, plus e to the 2x over x minus e to the x plus 1 over x. So that's the solution. You could also, if you like, this is all over a common denominator of x. I have e to the 2x, and then I have some constant times e to the x, where my constant is equal to b over e minus e. So the solution of this differential equation is exactly this. All right. So the homework for next week, I'm going to change it because instead of what I had originally put on the website, I'm going to change it to for you to solve some problems in ordinary differential equations. Let me just give one example of this because it is useful in PDE. Remember, in PDE, this first equation that we've been looking at is the heat equation, which says that the partial, if he is the heat of somebody, the partial of u with respect to t is some constant times the second derivative of u with respect to x. So this is the heat equation in PDE. This describes the flow of heat, transfer of heat in a one-dimensional, it's a one-dimensional heat flow. And when we solve the heat equation, it ends up being reduced to something. Actually, we're going to derive the heat equation. And the derivation, among other things, uses, besides conservation of energy or conservation of heat, Newton's law of cooling, which you must have seen before, because this is one of the basic examples at Lehman, at least, in first year calculus in Math 176 in differential equations. And what Newton's law of cooling says is that the rate at which a body changes temperature is proportional to the difference between its temperature and the temperature of the surrounding medium. So suppose we have y is f of t is temperature of some body at time t. So you have some body, this is something you're measuring, temperature of the body at time t. And the body is sitting in some environment. Here's your body, and it's sitting in, actually, you see this all the time if you watch Law and Order. The body is a dead body and it's lying in a room. And the medical examiner comes in and the detective says, what time was this person killed? And the medical examiner says, This person has been dead for approximately 10 hours. How do they know that? Easy. Newton's law of cooling. Newton's law of cooling says that the rate of change of the body's temperature is proportional to the difference. So let's say this is the medium. M of T is the temperature at time t in whatever medium, whatever space your body is located in. So if Y of T is the temperature of the body and M of T is the temperature of the surrounding medium, this is the temperature difference between the body and the medium. Now, suppose the body temperature is hotter than the temperature at the medium. This is going to be positive. You think of the medium as being so big, the temperature isn't going to change very much. You look at the difference between the body if the body temperature is higher than the medium's temperature, it means this is positive. You expect the body to cool. So dy dt will be minus, it'll be negative. And exactly how it's negative is Newton's law of cooling. Newton's law of cooling says that for any body, there's some positive constant K, such that the rate of change of the body temperature is proportional to the temperature difference between the body and the external medium. So if you're in a room which is at 70 degrees and your body temperature is 96 degrees, 96 minus 70, that's a positive number. What keeps your body at 96 degrees? It's all the metabolic processes going on in your body. You know, your heart is pumping blood. The blood has nutrients. The nutrients are absorbed. The cells convert them into energy. That maintains your body temperature. What happens when you die? Your heart's not pumping blood. The cells in your body don't get any nutrients. They stop producing energy. Your body is cooling. Your body is 96 degrees, and there's no reason for it to there's no way it's going to maintain that temperature. So according to Newton's law of cooling, you know your body temperature will drop and it will approach the temperature of the medium of the room. And by looking at this equation, what the medical examiner does, takes a thermometer, checks the room temperature, checks the body temperature. They know the constant K, assuming the person was, no matter how healthy or unhealthy you are, your temperature is not going to differ very much from 96 or 98 degrees. A couple of degrees isn't going to matter. You can figure out from the solutions of this differential equation how much time had to pass until your body temperature is dropped to whatever it is. So this is Newton's law of cooling, or we can write it as y prime plus ky is equal to k m of t. So y is the temperature of the body, and it satisfies this ordinary differential equation. It's first order, because you only have a first derivative. It's linear, because you just have y prime and y. And it's not homogeneous, because you have this function, which we would call q of t, on the right-hand side. What's the solution of this differential equation? Well, since we already did all the work, here is my general formula for a solution. Let me call the solution, I'll call it u instead of f or g, and the variable is time, u of t. Sorry, f of t. But it's not f of x. So we want to find a solution, u of t, f of t. So f of t is going to be equal to b e to the a of x. So what is my function p? P of t is just the constant k. A of t is the integral from a to t of k du. That's just equal to kt minus ka. So we have b e to the minus kt to make this 0. So be to the minus kt plus ka plus e to the minus a of t, the integral from a to t of e to the a of t times q of x. So I have q of t is km of t dt and km of u du. Just want to follow the notation in the notes. E to the ku. So there's actually, I'm looking at the notes. The notes, that's the book that I scanned and sent out to you. I think I made a little mistake here. So what I've written is correct. But the important thing is Newton's law of cooling, because we're going to see that again when we try to derive the heat equation and partial differential equations. So the important thing is the differential equation. It says that if you have a body immersed in some medium, like a human dead body in a room, the room is the medium. And if y of t, if f of t if y is the temperature at time t, the rate of change of the temperature dy dt is proportional to the temperature difference between the body and the medium. So y minus f of t. This is measuring the body temperature. If the body is hotter than the room, this is positive, the temperature will decrease. That means dy dt, the derivative is negative, it's minus k. If the body is cooler than the room, if the room is hotter, this is going to be negative, negative times negative, positive, and the body will warm up. So if you put an ice cube in a room, the room is warmer than the ice, the temperature of the ice goes up, the ice cube melts. If you put hot tea in a room, and the hot tea is hotter than the room, then the tea will cool. So this you know without any calculus, but the fact that the rate of change is proportional exactly to the temperature difference, that's Newton's law of cooling. And that is a fundamental fact. So, okay. Are there any questions about this? We're going to have to do a little bit more about ordinary differential equations before we go back to looking at the heat equation. But I will send out by email and post on the Blackboard what the next homework assignment will be. And it will involve solving some ordinary differential equations. Okay. Questions before we quit for the day, for the week? No class on Monday, it's Labor Day. So the next class is a week from today. Okay, everybody. Have a good weekend. Bye.